Okay, so we're 30 seconds early, but the green light is on.
All right, so I'm there.
So it's my pleasure to introduce Josh to tell us about isomorphism, derivations, and the representation.
Thanks, Alan. Of course, I want to thank the organizers for running this excellent program here at the Institute and for inviting me to speak today. Yeah, so I want to talk about isomorphism, derivations, lead representations, and this is joint work with Pete Brooksbank, Uriya first, and James Wilson, though in different projects. You'll see which theorems get cited and where they are. But this has been a lot of fun. It's culminating in a great amount of work. And well, let me actually just get started with a fun example. So I'm just going to assume K is a finite field. You can work more generally, but all my complexity results will be assuming finite field. So let's say we're given generating sets for the two groups, and given by this. Upper triangular matrices here. So the star just means I can put anything there, and then I'm not going to just write a bunch of zeros because I don't want to. Okay, so I'm given this. Okay, and the numbers here work out quite nicely so that any sort of quick back of the envelope checks that you try to do, you realize that these groups could maybe be isomorphic, and the question I want to ask is, I want to decide if maybe I'll call this here and maybe I'll call this H. Decide if G is isomorphic to H efficiently.
The stars don't mean all possible entries in there, do they?
Yeah. So this would be corresponding to a 2 by 7 block. Yeah, put anything in the field you like there. Yeah, so the question is, well, I guess the problem is decide if these two groups are isomorphic efficiently. And you could, scramble this thing up. It doesn't have to be given in this upper triangular way. You can, conjugate, generating set, whatever. The goal is to not have to understand what the group is. The goal is to do this computationally effectively. So if you like, you could sort of scramble the gen set by conjugation, by conjugating an invertible matrix. Okay, so it's not necessarily given as the way I've written it, but that's sort of the abstract. Okay. But a related question to this. So for this group G, are the numbers, this is color. Oh, here's color. Blue's okay, right? Is blue okay? The blue's okay. For the group G, are the integers 2, 7, and 6 significant? This is a bit of a vague statement, or a question. Are 2, 7, 6 significant? G, and just to give an example on a trivial case where such integers wouldn't be, think of the abelian group. This is isomorphic to this. The pair of integers are totally not significant to this group. There's no way they're meaningful. So I mean, if these three integers were significant, then of course these two groups wouldn't be isomorphic. Okay, just a spoiler, these two groups are not isomorphic. G is actually not isomorphic to H. Decide so efficiently. That's really the task. Okay, so I want to just take a little bit to talk about group isomorphism and just kind of set up some of the background here. So, because of theorems of Novikov and Boone, and also throw on Avian and Rabin, isomorphism in general for finitely presented groups is undecidable. So we restrict our inputs to purely finite presentations. We're not going, I'm sorry, we want to exclude finite presentations. So because of this, let's say our groups are input via, okay, first model that we'll work with, that I don't mind working with, is a subset of the general linear group, N over FQ. These would be the generators. There's a bit of an issue here that we have to deal with. The discrete log is still a problem in this case. If you bound the prime, then you don't have to worry so much. Let me just say this. This is Lux 92, or we can take our inputs as quotients of permutation groups. And this is following Cantor and Lux in 90. Okay, so this is just a way so that if I talk about polynomial time complexity, I'm not dealing with some sort of input model that is going to, be either exponential when I just multiply elements, or not necessarily have polynomial time algorithms for some of the basic computations I need to do on the group theory side.
Sorry, Josh, I'm confused.
Yeah.
What did Lux 92 show about things input?
Oh, that you have a lot of so a lot of the basic algorithms like membership testing,
Okay.
all that sort of stuff are in polynomial time with some say with some conditions on the order of the group. Yeah, if you bound, I think, the largest prime that divides the order of the group, then you don't have to worry so much about discrete log problems. Other questions? No. Okay. So, okay, that's good. Yes. So, following algorithms of Cannon and Holtz and Ike, Liam Green, Brian, I'm going to basically work with this group for the time being, but we'll work inductively down a characteristic. I'll even have the word nilpotent series. So, in this particular example, I'm just going to work with these groups, and I'm just going to write the lower central series here. Of course, you could use a better series or a series that you prefer. I don't care at the moment. I just want to write down a series, and the lower central series is quite nice because just thinking about these two examples right here. I have other colors. Okay, maybe I just have blue and red. Well, gamma 1's the whole group, and gamma 2 is just going to be this little piece there, this little piece there with zeros on that piece there. Okay, so it's a bit easy to visualize this lower central series. So they work down this nilpotent series, and they go and construct isomorphisms or automorphisms in a kind of an approximate way, looking at successive quotients. A problem arises with these specific groups. I've just hit everything. Problem. I'll just kind of back a little bit. With the above example, one needs to search through GL56Q, which is just not going to finish. Okay, we'll see this problem come up again in a slightly different context. But, so what do? I mean, you could just stop and say it's not going to happen, there's just no algorithm to do it, but maybe you're stubborn and you just want to figure it out and you just want to decide this isomorphism or this non-isomorphism in this case. So,
Wait, sorry, why are you searching through GL56?
oh, I'm not really giving all the details, but so what one does, and you'll see this again. So you look at this quotient right here, and this is an abelian group. In fact, it's a vector space because things work out nicely here, and this is just exponent p. So you have this vector space, and if you want to decide isomorphism, you could first do it on this quotient. The isomorphism between these two vector spaces, now you've got this.
Oh, right, so you're
56.
multiplying these numbers together.
14 plus.
Yeah, that's right, yeah.
Yeah. I wasn't sure how you got 56.
Got it. Oh. So the question was about 56. 56 is 7 times 6 plus 2 times 7.
I'm on it. Thank you.
Got it. Okay.
Wow,
Sorry.
this is real bad.
Well, these numbers, these two triples are really quite nice. I mean, 56 happens here, 56 happens here. They both sum to the same thing. If you add their squares, they get the same thing. I had to do a little bit of math to get those things. So, okay, what now? What was it? Oh yeah, right. Okay, so one thing you can do, I'm just gonna have to hide it for a moment. Maybe I could do this. That works. Okay, so what now? Well, one, you could refine the series with more characteristic subgroups. Okay, you can use generalized filtrations. Where you've got, your index set here, index set given by a semigroup that is partially ordered. So that's just what I mean by generalized filtration. Yeah, so in this case, maybe I'll say this. In this case, under certain conditions, and this is not something I'm going to talk about in this talk, but I'll just mention it. Under certain conditions, the associated Lie algebra I'll say no, not the associated the automorphisms or isomorphisms, the autos or isos of the associated Lie algebra lift to autos, automorphisms or isos of the group. This doesn't always happen because, well, when you work over semigroups that are partially ordered, you could have a lot of crap happen. In particular, you could actually make the associated Lie algebra from this filtration totally trivial. Not a topic that I'm going to talk about for this talk, but I'm just saying that we can handle the isomorphism. This is done in 2018. Further, what one can do, and what Pete, okay, this is challenging. There we go. Brooksbank, O'Brien, and James Wilson showed, I think this is 2019, showed that a large family of groups are amenable to such filtrations. yielding in polytime in the order of the groups, not necessarily order of the log of the order of the group. Polytime in the order of the group, so it's still an improvement, still an improvement of the general case. Yielding in polytime for isomorphism testing. So, I think I run the course there. Okay. So, well, that's one thing you can do. You can refine this series. There's evidence that when you come up with P groups, sometimes they are amenable to such methods, and sometimes you can get a lot out of it. Refining these series quite well. But sometimes that just isn't the case. Sometimes you can't find anything. And I'm going to write this as the hope is that there's a reason you can't find it.
What does anything mean?
Anything as in no characteristic subgroups. Hopefully you can find them. Yeah, okay, characters. The hope is there's a reason for this. If you can't find anything and there isn't a reason, then you're just really out of luck. I mean, there's just, well, welcome to the world of isomorphism testing, I guess. That's just sometimes what happens. So the hope is that there's reason for this, and that's sort of the camp of groups I want to focus on today for this talk. So, erasers. So what kind of structure can we take advantage of? We can't find anything, and we still under this problem of having, say, to run through a very large GL, for example. Now we'll talk about bilinear maps. So the commutator let's maybe say, yeah, so let's do that. Gamma S plus 1 cross gamma T plus 1 into, that gives us a biadditive map. And well, since we're dealing with P groups here, and we've got this Q, this is a FP bilinear map. I'm not going to say that it's so obvious. I mean, okay, it is FQ bilinear, but it may not be given in such a way. It may be written as just a standard P group, say, over the prime field. And oh, that's beside the point. FP bilinear for sure, but biadditive. Okay, so if I have an isomorphism, from G to H, this induces an isotopism of bilinear maps. For example, maybe I'll put a G there. I'm just going to write U, I'm just going to write V, I'm just going to write W, so I don't have to write all that again. And if the commutator on the H is not also equal to U, V, and to W, then you're already done because they're not isomorphic. This is going to induce an isomorphism from there, and from. So this is what I mean by an isotopism, something that does this. And it satisfies the right property when I multiply two elements here, get over to this W, and then I apply this. That's the same as first applying these two, then multiplying over here, getting over there. Okay, so that's what an isotopism is. And if I have an isomorphism, it'll induce an isotopism. So the hope is maybe we can study this bilinear map to understand something about these isomorphisms. So here's where we can kind of see the problem arise if I have a bilinear map now. Let's just drop the subscript and superscript. If I have just a bilinear map here, it factors through the tensor product. I'll go back to K. Right, and so now what's happening is, well, I'll maybe label that as a tensor product, and there's this F here. This map has a kernel over here, and now if I want to decide isomorphism or automorphism, I'm thinking about how this kernel is being moved around by the group GLU, GLV. If I want automorphisms, if I want autotopisms of this sort of thing, I'm looking at this kernel and trying to stabilize it. If I'm looking at isotopisms, I'm just trying to get them under the same orbit, under this group, acting on this space. Okay, and here's where the problem comes up again. I've just moved the problem from this algorithm to bilinear maps. Okay, there's a symmetric version here where I have V cross V into W, for example, and then you might consider the exterior square, but that's just not really that important. I'm just going to leave them general. So, one way to maybe fix the problem. So this thing is rather large. This thing is rather large. It'd be nice to have a sort of thing that can fit in here that's really quite small. I want a tensor over something larger. Than just K. And so, well, there's such an algebra that will do this. I'm going to label this M. And this will be the algebra where I just have matrices here. This X is going to be inside M U. Matrices. Whoops, not Y. W. And I'm just going to put a little op there so that it turns into a ring, such that for all U and U and little V and V, we have that. Okay, this is known as the adjoint ring. Adjoint ring. Associated to, of course, I maybe haven't labeled it, but it's associated with this bilinear map, this bracket, and it has the excellent property that it is universal, right? Meaning, if I tensor over any other ring, tensor over U and V, over any other ring, it will embed that, such a tensor product will embed into that. And so this is going to be the largest ring for a tensor over this universal product. So in some sense, this is an optimal choice. This is optimal for this diagram. Excellent. Okay, so maybe I get lucky. Maybe I get lucky, and maybe this M has a lot of structure that I can take advantage of. If this thing is rather large, then this thing, well, we hope is going to be quite small. I don't know how small, maybe small. Okay, now the next problem, is deciding, well, okay, so you've shrunk the space, you still have this GLU cross GLV acting, and this may not act on that space in the way that you might want. So what it does? Well, just the normalizer event. I'll write down what I mean in just a minute. say M here is a unital and associative algebra. So it's really quite nice to work with. So, the group acting on this space U tensor over MV is just the normalizer. These would be all the things in the GLU cross GLV, such that, all right, for all x, y, and m, x conjugated by A, y conjugated by B is inside of M. So this is the group that acts on this space. Because M is a unital associative algebra, we can just construct this thing. It's not exactly easy, it takes a bit of time, especially when there's radicals to deal with. But since, maybe I'll just say since, unital and associative, we can construct this.
The exponent A meaning.
Conjugation. So, I've alluded to this before. There's a symmetric version of this diagram over here. The symmetric version would change this definition only slightly, where I need A to be equal to B. That gives me a star algebra, and there's some extra structure I have to worry about there. But I'm just going to leave it quite general here. Okay. Right, so these two tools inspire the proof of this theorem.
Actually, sorry, Josh, can I add? So when you say construct this group, do you mean like you can find generators for the group? Is that like?
Yeah, that's right. That's what I mean. Yeah, I mean, actually, for a Pete and James worked out in significant detail how one would construct this group, and for this next theorem, we definitely need to construct this, and this level of details is quite useful. But yes, when I say construct this group, I mean give generators. Okay, theorem here. So K is going to be FQ, and this has to be odd. Instead, I'm given two bilinear maps. I'm just going to keep using the bracket notation. And these are alternating K bilinear maps. Decide if the first one is there exists an extension E over K such that the two K bilinear maps are actually E bilinear with the dimension as an E vector space of W is 2. Well, you gotta do that. I'll move it in a sec if you miss the top for some reason. And if so, decide if these two bilinear maps are isotopic. Oh, and of course, that's not just a decision time. These algorithms are in polytime of the order of,
When you said isotopic, you mean over E over K over E over what?
Right, and time polynomial and what?
thank you, time polynomial in the dimensions of these. Dimensions over K of V, K of W. Let me add a Q in there as well. One can get rid of the, oh, but I need the extension, that's right. Got it, the extension. And the degree of the extension. One could get rid of this Q with a bit of bounding, a rather technical thing that I don't really want to get into. But then you have to worry about some other things. So, what does this tell us? Okay, so this was about isotopism, K-isotopism. So a corollary to this, just so I don't forget something. Decide iso of odd order P groups of class 2, X prime P.
Could you finish the word ISO? Thank you.
Just enough space. Yeah. Isomorphism. Yeah, I'm going between isotopism and isomorphism there. So that isomorphism odd order P groups of class 2 exponent P whose commutator satisfies this first thing. It comes back. Oh, let me say satisfies 1. So
So
here,
in the term, if there is no extension, then you can say nothing.
sorry, what was that?
So in the term, is that completely clear? If there is no extension, if one fails, then
Yeah.
you cannot do anything.
That's right. That's right.
Okay.
Can't do anything. Yeah. Yeah. In particular, we really need that dimension to be 2 over E. So, I mean,
you need just at most two.
okay, yeah, at most 2, yes. When it's 1, then I'll give that to I think it was Lewis Wilson that maybe does that. But yeah,
That's been done for years.
yeah, it's yeah, that's right. The new thing here is the 2. It equals 2. But sure. Whose commutator satisfies 1. So what I mean by satisfies 1, I mean K here is the prime field, and W would have to be, there would have to exist some extension such that W is 2-dimensional with such an extension. Not finished with the sentence though. This isn't anything. Commutator satisfies that isn't one at a time. Runs in polytime. In, let's say, log G, oops, log G prime. And I think I need,
Are you sure you mean log G prime?
Yeah, I
Expanded
mean-
by log G.
give me a moment. Yeah, of course. No. I'm sorry. Kind of by this. So it's going to be, yeah.
Okay, that makes more sense.
Yes. Sorry. Okay. So this needs to get thrown in there if the extension field gets to be rather large. One has to deal with this one. Okay. So, right. This M, I guess it's no longer there anymore. But the M and this group here basically give us a ton of control over the bilinear maps that satisfy this condition that are bilinear over some extension with the codomain two-dimensional. And this gives us a lot of structure to work with. Okay, but my question is, but why M? Why this ring? And maybe draw a picture right here. If I move everything over to one side, turn it into a trilinear form. Something like this. M here was kind of just acting on these two. There's no reason to just think about these two. I could think about these two, or I could think about another pair. So, okay, I have one picture right here. Whoops. M. I have another picture right here, and I don't want to have to think about the labels. And I'm just going to call this L. It's defined in a very similar way to M, not important for this talk, the actual definition of it. Such an algebra exists. And I have an R. So I've got these three things. Okay, why M in this example? Well, if you look at these bilinear maps over here, sort of weighted very heavily to those V's, right? The V's could be anything, but I'm bounding the dimension of the W's. So I might get a bit acting on the two V's right there. That would mean that M could be quite large and maybe L and R might not be. But there's no reason, if they're all roughly the same dimension, why choose one over the other? So the question still stands, why M? Or why, what is there any choice here? And notice that this M is only acting on two, this L is only acting on two, and this R is only acting on two things. You could put two of them together, right? I can think about maybe doing tensor product here over M, maybe a tensor product here over R. But then I can't quite get the L into the picture, and I want to somehow get them all into this picture. If I have structure here, here, and here, I want to take advantage of it. Now I want to talk about derivations. And this will kind of address this thing that I just mentioned. So, the derivation algebra. Has a very similar definition to ring M. These are going to be endomorphisms. I'm not going to write them out. This is the endomorphisms of U, V, and W, you'd expect. Such that for all U, and for all D and V, the following equation holds. Okay, so it satisfies this derivation-like equation here. The nice thing about this derivation acts on all 3 bits. There are other ways to get all 3 bits acting, but derivation is a sort of a natural choice here. And as this next theorem is going to show, that this is actually somehow the best of these linear algebras. So this is the theorem first self-James. And the statement of this theorem is going to be a bit vague because there's a lot of notation and definitions that aren't really needed anywhere else in this talk. So I'm going to write down something and then I'll give some meaning to it. So among algebras, and U and V and W acting on bilinear maps of the form U plus V into W. via linear constraints. I'll describe what I mean by this, but what I mean by, oh, maybe I'll do that right now, actually. What I mean by linear constraints here is an equation like this, where I have just an x plus just the y plus just the z. And with the m, it's no longer on the board, but the m was something like, I think there was an equal sign there, and then this thing wasn't in the picture. So it was just an x and an equals y. That's what I mean by linear constraints. So algebra is defined in such a way that active bilinear maps via these linear constraints, the algebra of derivations, D, is optimal. As in, maybe I'll say this. That is, for sufficiently large K, all such algebras embed. So this is what I mean by optimal. Why do we care about linear constraints? At the end of the day, we want to be able to compute something. And linear constraints means that I can compute these algebras via linear equations. I don't want to keep fishing around, though. I don't want to have to compute a whole bunch of unnecessary stuff and then try to make a decision based on some amount of data. I would like there to be a best choice.
By the way, this theorem is Q still odd? P or P?
Well, okay, so I need, no, it's not, but thanks for asking. Sufficiently large, in this particular case, so this is a general theorem for general multilinear maps. Sufficiently large here, I guess just means K not 2. So, that'll be sufficiently large for this.
And Josh, in your corollary, do you assume you have this field E given? When you say it satisfies property 1, do you assume
No.
this? So you don't need E for this, you just need to know that it exists.
E being the extension.
Yes.
Yeah, no.
The previous thing said you find it in the one.
Yeah, the extension field we compute.
Yeah, but it would.
I'm erasing something. What?
I mean, you assume this has been done, and then the new complexity is only that. I mean, this doesn't account for the complexity of finding.
That is the complexity is basically just going to be in log G. Log.
But really what you're counting there is the complexity of running the algorithm specified.
Yeah, I mean, I put it at that, but the isomorphism is just so far outweighs the first one. The first one is just linear in the number of generators. The second one is, well, I mean, not linear number, polynomial in the number of generators. And the second one is polynomial in the number of generators plus a bit of extra fuzz down
Yeah,
here.
but this E shows up there, right? So if E is horrendously big, then.
Oh yeah, I see what you're saying.
What you're reduced to is still a problem involving GL2E.
I'm sorry, I missed the first problem.
Are you still not reduced to a searching problem?
Yes,
In GL2E.
exactly. Yeah.
So if E is large,
Hmm.
you're indeed in a situation where you still
Yeah.
potentially have a big group, but it's not nearly as big as GL56. It's GL2.
That's right.
And so this is, sorry, while we're on it, this is
Yeah.
constructive then, this last isomorphism, you actually construct an
Yes.
element that actually
Yes.
gives the other.
Yeah. So okay, for all the isomorphisms I care about, I want some map given. So I don't even consider it valid if a map isn't given, unless it's like maybe a Billinger's. Yeah. No, that's a good point. Good point. Right. Okay. Yeah. So that's okay. So the derivation algebra gives us a kind of optimal choice. So how does this thing fit? Well, you can't just put the derivation algebra into this diagram like I did there. So, well, just define a generalization. And this is what we did with James and I with Uriya first. So the denser subspace, which is a portmanteau of derivation tensor, and kind of a pun as well.
Is this due to James Wilson, this name?
Yes.
Yeah.
Of course
I'm
not.
not surprised.
Denser subspace of this is the following. Actually, the notation is definitely more to James Wilson. It's going to be the set of bilinear maps. So I'm just looking at all bilinear maps of this form. So going from U, V to W, such that the derivation algebra of this map that's given by these brackets is contained in the derivation algebra of this bilinear map. That's the denser subspace.
And these are supposed to be D's around the bracket?
Yeah.
These are backwards
D?
D's. These are backwards D's.
Yeah, I'm not so good at writing them, but yeah. You can think of it that way, or half circles if you'd like.
This comes from quantum stuff. You're supposed to think of Brack and Ket.
That's right.
Ah,
That's right.
okay, right.
Yeah. I've spared you notation of the Braun Ket version of the story, but yeah, that's sort of where it's coming from. That's right. Thanks, Bill. Right. So, okay, let's go back to that example that we were looking at, just to show non-isomorphism of first example. You could actually just go and compute their derivation algebras. One could actually just compute all these, L's, R's, and M's. But I'll do this for the first one, and there will hopefully be no ambiguity of what I mean by this. This one is isomorphic to GL2, GL7, GL6 over K. And the second one is isomorphic to, sorry I'm hiding this. I'll bring it up in just a second. I'll bring it down in just a second. So those are the derivation algebras. That actually answers our first question. Second question, I guess. Are the integers 276 or 384 significant to these groups? The answer is yes. One sees them immediately in these derivation algebras. Now, the nice thing, these things are large. So their densers are small. And in fact, in these examples, their densers are one-dimensional. Best as we could hope for. Right? The tensor that the bilinear map, I'll let my tensor slip there. The bilinear map that's inside, that we're computing the denser subspace, is already going to be inside of this. So it's going, unless it's the zero.
One-dimensional over what?
Over K. Over K. If I don't write the K, you can, well, no, just ask. That's there are E's sometimes there. This bilinear map is always inside of this, trivially, because it contains its own derivation algebra. So this is really the best we could hope for in this case. Like before, when we looked at a different space, where we looked at a smaller space, we had to think about the group that was acting. And here, exactly the same sort of generalization occurs. The group acting is a normalizer. I'm going to be a little bit sort of lazy with my definition here. So A, B, and C, these are invertible matrices. And for the next part, they'll have to be for it to make sense. For all x, y, z, d, exactly what you expect from before has to hold.
I'm sorry, what is the group acting? What does this expression mean?
group acting on this denser space right here. So the GL, U, V, and now you gotta have W also acting on this. You can't just have these two. It may not be the entire whole GL. And it may not even be anything like the normalizer of M. You'd have to go even smaller and normalize this derivation algebra. Now, if it isn't already clear, this derivation algebra is a Lie algebra. And well, it's no longer the word, but when we computed this N of M, we took advantage of the fact that it was an associative unitary algebra. Now we're trying to normalize a Lie algebra here. And this is in positive characteristic. So this gets very hard, very hard. But I will get to that in just a minute. First, I'm going to move this up. So, computing this normalizer, in this case, when we have a really small denser, in fact, one-dimensional, basically tells us everything we need to know. But let me give you the proposition that says so. Same paper. So suppose I have two binomial maps again. Again, going from U cross U to W, K bilinear. And there exists an A, B, C. I'm using this notation on purpose to think of this, but I want these to be invertible matrices such that for all X, Y, Z, and I'll do the superscript 1 to be the derivation algebra of that one, of the first binary map. For all of this, X, A, Y, B, C, Z. Oh, backwards. If that is true, is that not? Yes. Then are K isotropic, these two bilinear maps, if and only if they are in the same ND orbits. I'll describe what I mean. Due to time, maybe I'll not say too much. But basically all what's going on right here, if I have two bilinear maps, and I want to show or decide whether they're isotopic or not, I'm going to need, as a result of that, I'm going to need their derivation algebras to be conjugate. I need to have some sort of conjugating element. If they're not even conjugate to begin with, they're not even going to be isotopic. Okay, so if I've got this here, if I have a conjugating element from one derivation to the other, then I can just identify these, identify their denser subspaces, and then see if these two bilinear maps inside of the denser subspace, I'm saying the now because these two have been identified, if they're in the same orbit, then I'm done. I take this conjugating element plus whatever element from ND that takes me from here to here in that denser space, and I've got myself an isotopism. That's the whole idea right there.
So this means you're doing some search through like a symplectic group? Is that the point? If you're trying to identify these maps, or is it just has to be in GL?
Well, I don't know. It has to be. So I'm not so sure if I understand what you're asking. This may not be a symplectic group. It could be. I mean, I guess things could happen, but it's just a normalizer of some Lie algebra. So it's.
So where are the ABCDs? Is just any three invertible?
Yeah. So this is going to be in GLU, GLV, and GLW.
Okay.
Yeah. Any in there. fact, every Right. So when you have a small tensor, the idea is to then you win actually, and you use this theorem. This is Brooksbank, Wilson. So here's the idea. So again, I've got 2k bilinear maps. With the derivation algebra, I'm just going to identify this with. So I've got two derivation algebras that are isomorphic. Where D is a simple Chevrolet. Any other ones? The algebra. Oh, you know what? I'm gonna need K. I'm gonna need the characteristic of K to be at least. I think I need at least 5. At least 5 will do. 2 and 3 give us problems. 5 should do it. If not, 7 will do it. No, 5 doesn't. 5 doesn't. Where D is a simple Chevrolet algebra. Very good. If U, V, W are irreducible D modules, there exists polytime algorithm to decide 1 if these two are conjugate in such a way like this. I'm just going to use this twiddle here. 2, if so, and the dimensions over K are bounded by a constant.
Of the DI. Dimensions of what over K?
Dimension. Oh, I didn't write it. I said it, but I didn't write it. Dimensions of tensors. Sorry. The dimension of the tensors bounded by a constant. Then decide these are K isotopic.
What's polynomial time coming up with a constant mean? I'm quite understand what the logic there.
I don't understand the question. Sorry.
Well, there's a polynomial term and there's a constant. After there's a constant and
Yeah, so if these densors, if the densors are going to be, the dimension of these densors are going to be bounded by a constant, then we can decide isotopism and polynomial time. Yeah, so maybe I should have switched the order there, but the constant comes before that. And the whole reason that we can do this is because we kind of understand a little bit of the representation theory. To do this, we rely very heavily on computing Chevrolet bases using algorithms from Rob Wilson and Alex Riva as well. That is quite fundamental to this approach. Running out of time, I just kind of did want to use some examples here. Leave myself just that. Right, so the examples. So we already had that first example. The dimension of the tensor subspace is one-dimensional, and so we could very quickly get autotopisms or isotopisms straight away from their derivation algebra, straight away from this algorithm right here. we can construct a given Lie algebra L a group or a GL on the set L cross L. You define the multiplication A plus C, B plus D plus 1/2 of the bracket. So you're not in characteristic 2, this will work out. Okay, so this defines some group on the set L cross L. And the nice thing about the commutator here is it's going to be exactly equal to the bracket there. If L is simple of types A, B, C, D, the denser dimension is bounded by 2. So here's a family of groups for which we cannot, aside from using this algorithm, we cannot find any characteristic subgroups. So maybe we can get lucky and find a few. But it's rather difficult to decide isomorphism of groups in these families. Yet these derivation algebras, because the denser dimensions are bounded by a constant 2, in fact, their derivation algebras are telling us basically everything we need to know about their automorphisms, or autotopisms, or isotopisms. So, just to wrap up, yes, you can refine series, find characteristic subgroups, and when you have a group that's amenable to that, yeah, sure, that's a great option for deciding isomorphism. But sometimes you just can't find any characteristic subgroups, and sometimes there's a reason, like for groups that come like this, or like groups that come from the example I started with. And for those kinds of groups, we need different tools. And the derivation algebra seems to give us a way out for certain families of these kinds of groups where these things show up. So thank you so much for your attention.
Anyone have any more questions?
Okay.
It may be worth trying to state the corollary, which is a very nice corollary in a form which people might easily identify with, which is that you're taking a D-generator P group of its form P.
Yeah,
And order P to D plus 2.
that's right.
And if you're
Yeah.
given two such groups, you can decide isomorphism at the cost of looking through GL to P, which is a significant way. And that's, for a P group theorist, that's the way that it naturally arises.
Yeah, yeah.
If you'll get such a group of order P to the D plus 2 for any quotient rate D.
So you're talking about the
corollary.
genus 2 theorem.
Yeah, I
yeah,
know
that's right. That's
genus
right.
two.
Yeah. So right, if you give a group whose W, so you think about that bilinear map that we had. Yes. With B cross B to W, if the W is just two-dimensional over the ground field, then there's no extension that would be there, and then yes, of course, this will be a D-generated group, roughly of order 2 to the, P to D plus 2, and we could do that in a
Not roughly, it
No,
is
yeah.
exactly.
Sort of stupid historical comment. For those of you for whom the word isotopism or isotopic is a foreign word, when U equals V equals W, this whole business of bimap is a non-associative algebra, as you just got there. And in the 30s and 40s, Brock and A. Albert studied those algebras, needed an equivalence relation, and they defined and studied the word isotopism, which is exactly this, but specialized quite a bit.
That's right. Yes.
So these guys did not invent the strange word.
No, that was from. Yeah, that's right.
Okay, well, let's thank Josh again.
Let's leave the front door of the meeting institute in 10 minutes. Table for lunch before